4 astronauts disappeared behind the moon. No signal, no communication, no way to call for help. For a few minutes, they were the most isolated humans in history, cut off from every other living person, with nothing but their instruments, and the math that would bring them home. They were over 250,000 miles from Earth, deeper into space than any human had ever gone, watching the surface below them get struck by objects moving faster than rifle bullets. And then they rounded the far side, the side no one on Earth ever sees. And what they saw didn't match the images. The surface looked unfamiliar, almost unreal. One of them broke the silence and said something that made everyone listening stop. Humans probably haven't evolved to see what we're looking at. At that moment, first experienced during Apollo 8, was the first time humans ever saw the moon's hidden face with their own eyes. And now, with Artemis II, we're about to go back. But this time, we're not just passing by. We're going with better instruments, better understanding, and questions we didn't even know to ask the first time. Because the far side of the moon isn't just another landscape. It's a place that forced astronauts to question their own senses. And what we're about to learn from it might change everything we thought we knew about our closest neighbor in space. On April 6th, 2026, 4 humans, their names are Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. They were traveling farther from Earth than any humans before them, and arcing around the moon on a path that would take them approximately 252,000 miles from home. And as they rounded the far side, the side of the moon that has faced away from Earth since before our species existed, the last radio signal faded and the silence became total. For roughly 40 minutes, NASA could not hear them, could not track them, could not confirm whether integrity was still intact, whether the crew was still breathing, whether the mission was still proceeding as planned. Mission Control in Houston sat with its instruments and its charts and its coffee cups and simply waited, because that is all there was to do. Physics would either work or it would not. The mathematics that had been checked and rechecked and verified by thousands of people across decades would either hold or it would not. And until Orion came back around the other side, no one on Earth would know. What the crew saw during those 40 minutes, what they experienced, what they felt, and what they found on that hidden surface is the subject of what we are about to explore together. And I want to warn you gently before we begin. This is not a story with a tidy ending. The moon, it turns out, is not the simple, silent, well-understood neighbor we have always assumed it to be. It is strange. It is violent in ways that are invisible from Earth. It is asymmetrical in ways that still puzzle scientists. And the far side, that perpetually hidden face, is not just different from the near side. It is different in ways that reach back to the very beginning of the solar system, to a catastrophe so enormous and so ancient that its echoes are still visible today, baked into the stone of a world that has watched us from the sky for 100,000 years of human history. So let us go slowly. Let us take our time, because this story deserves to be told in the way it was experienced, quietly, gradually, with a growing sense that the familiar is becoming something else. The moon has been with us forever. That is the first thing to understand, and also the easiest thing to forget. It was there when the first creatures looked up from the ocean and registered something bright against the dark. It was there when our ancestors traced patterns in the sky and built the first calendars and planted crops according to the rhythm of its phases. Every poet who ever wrote about the night, every lover who ever looked up at a pale circle and felt something they couldn't name, every child who ever asked their parent why the moon follows the car, all of them were looking at the same object, the same face, always the same face. This is not a coincidence. The moon rotates on its axis at exactly the same rate that it orbits the Earth, a phenomenon called tidal locking, and this synchronization means that one hemisphere of the moon always faces us, while the other always faces away. From the surface of Earth, you will never see the far side. You never have. No human being who ever lived before the space age ever saw it, It was the great hidden face of our closest neighbor, and for all of recorded history, it might as well have not existed. The first humans to see it were the crew of Apollo 8 in December 1968. Frank Borman, James Lovell, and William Anders became the first people to leave Earth's orbit, and the first to travel to another world, the first to see the far side with human eyes. And what William Anders reportedly said when he saw it was not a scientific observation. It was something simpler and stranger than that. He looked down at a surface that no human eye had ever processed before, and said that it looked like something that had been run over by a lawnmower, broken, saturated with craters, completely unlike the face of the moon they had always known. The near side, the side we see from Earth, has smooth, dark regions, ancient volcanic plains, vast and relatively flat, that the early astronomers called Maria, the Latin word for seas, because they genuinely thought these dark expanses might be bodies of water. They are not. They are solidified lava flows, billions of years old, have vast sheets of basalt that cooled and hardened and left the near side with a kind of patchwork beauty, dark plains alongside bright, cratered highlands, the features we recognize as the man in the moon or the rabbit or whatever shape our culture taught us to see. The far side has almost none of that. The far side is almost entirely ancient highlands, saturated with impact craters, stacked on top of impact craters, a landscape that looks like the surface of a world that has been in a war for 4 billion years and never had time to heal. There are almost no volcanic plains. The terrain is rougher, older looking, denser, with the evidence of ancient bombardment. And for decades after Apollo 8, scientists looked at this difference and asked a simple question: why? Why are the two hemispheres of the moon so dramatically different? Why does one side look young and smooth relative to the other? Why does one side have ancient volcanic activity baked into its surface while the other is almost entirely untouched by lava? These questions turn out to have answers. But the answers lead to deeper questions. And the deeper questions lead eventually to the story of the moon's birth. A story so violent and so strange that it is difficult to hold in the mind all at once without stopping to breathe. We will get there. But first, let us ride with integrity. The launch was on April 6, 2026. The Space Launch System rocket, the most powerful rocket ever built by NASA, lifted off from Kennedy Space Center at Cape Canaveral, carrying Orion and its 4-person crew into a sky that was clear and blue and full of early morning light, and the vibration of the engines would have been felt for miles. The sound would have rolled across the Florida coast like a slow, low thunderclap. And then the rocket was gone, and 4 human beings were on their way to the moon. The first day in space is a peculiar kind of adjustment. The body does not immediately understand weightlessness. The fluids in the inner ear, which are responsible for the sense of balance and orientation, suddenly have no up or down to orient toward, and they respond with confusion that often manifests as nausea. The head feels full, because blood that normally flows downward under gravity now distributes evenly, pushing into the skull and the sinuses. The face puffs slightly. Everything seems slightly wrong in a way that is difficult to articulate. The body is functional, the mind is sharp, but there is a persistent sense that the environment is contradicting something deep and biological in your understanding of reality. This passes, usually within a day or two. The body adapts. And then space begins to reveal its stranger qualities, the ones that are not about discomfort, but about perspective. Through the windows of Orion, Earth was shrinking. This is a fact that astronauts consistently describe as more emotionally powerful than they expected. The planet they had lived on for their entire lives, the planet where every human they had ever loved still lived and breathed and went about their days, was becoming smaller. Not metaphorically, literally. They could watch it happening in real time, could hold up a thumb at arm's length and cover continents, could see the curve of the atmosphere as a thin, how a fragile blue line against the black of space. The Earth that looks so enormous when you are standing on it, that feels so permanent and so solid underfoot, was revealed to be a modest sphere, suspended in nothing, keeping itself together through gravity and accident. And the moon, ahead of them, was growing. Day 2, Day 3. Checklists and course corrections. Communication with Houston through the Deep Space Network, the array of enormous radio dishes scattered around the Earth that allows NASA to stay in contact with spacecraft far beyond our atmosphere. The voices from Mission Control would have had a slight delay, a fraction of a second at first, growing longer as the distance increased. Light travels fast, 186,000 miles per second. But space is large enough that even light takes time to cross it, as the one-way signal delay between Earth and the Moon is about 1.3 seconds. Not enough to make conversation impossible, but enough to be perceptible, enough to be a reminder that the speed of light is real and finite, and that even communication has a cost out here. On Day 3, the Moon filled the window, and that is when things began to get interesting. What the crew of Artemis II saw as they approached the near side of the Moon was, at first, recognizable. The Maria, the Highlands, the familiar features that have been photographed by orbiters and landers and rovers for 6 decades. But they were seeing it in a way that no photograph had ever quite captured. In natural light through human eyes, from a distance that allowed them to see the entire disk at once and simultaneously perceive the details of the surface. And immediately, they began noticing things. The colors, for one. The Moon is not gray. This is one of those facts that sounds wrong until you see the evidence, and even then it takes a moment to accept. The Moon in photographs appears uniformly gray, because cameras struggle to capture the subtle variations in color that the human visual system is exquisitely sensitive to. But with human eyes, in natural sunlight, the Moon has color. The dark volcanic plains have a faintly blue or blue-gray tint. The bright highlands have a tinge of brown, even orange in some places. There are regions that look almost golden in the right light. The differences are not dramatic, not vivid in the way that Earth's colors are vivid. But they are there, and they are meaningful. Different colors indicate different mineral compositions, different rock types, different histories. This is something robots cannot do. This is one of the arguments for human spaceflight that often gets lost in the debates about cost and risk and the capabilities of modern robotic explorers. A camera can capture wavelengths of light, but a human eye processes visual information in a fundamentally different way, integrating color, texture, contrast, and context simultaneously in a manner that allows for real-time interpretation that no current artificial system can fully replicate. An astronaut looking at a crater rim can notice something unusual about its color and immediately ask a question. Is that a different kind of rock? Is there something here that the orbiters missed? In a way that no pre-programmed robotic mission can do. The human brain is, among other things, an extraordinarily capable pattern recognition system, and it works best when it has rich, real-world sensory input to work with. The crew of Integrity was noticing things. But before they could settle into observation, the Moon did something that none of them had anticipated. It was Commander Wiseman who saw the first one, a brief, bright flash on the surface below. He called it out, and the other 3 crew members came to the windows. And then there was a second flash, then a third. Over the course of their approach and their transit around the near side, the crew counted 6 distinct impact flashes. 6 moments when a meteoroid traveling at speeds measured in kilometers per second struck the lunar surface and released an enormous burst of energy visible from their position in orbit. To understand what this means, yet you need to understand something about what the surface of the Moon experiences on a daily basis. Earth has an atmosphere. Our atmosphere is, among its many functions, an armor. When a rock from space enters Earth's atmosphere, even a small one, a few centimeters across, it encounters air. Air molecules resist the rock's passage, creating friction, heating the rock to incandescence. If the rock is small enough, it burns up entirely before reaching the surface. What we see as a shooting star is not actually a star and is not actually falling. It is a piece of rock evaporating in our upper atmosphere, releasing its energy as light turned to vapor before it can do any damage. The Moon has no atmosphere, not even a trace of one, or rather, only the thinnest possible wisp of gas. Exosphere, technically. It had a scattering of molecules so sparse that individual particles rarely collide with each other. Nothing that could slow down an incoming rock, nothing that could burn it up. Every meteoroid that crosses the Moon's path Every piece of rock, every grain of high-velocity dust, every chunk of old comet hits the surface at its full cosmic speed. That speed ranges from about 20 kilometers per second on the slow end to 72 kilometers per second on the fast end. For reference, a rifle bullet travels at roughly 1 kilometer per second. The slowest meteoroids hitting the moon are 20 times faster than a rifle bullet. The fastest are more than 70 times faster. At those speeds, even small rocks carry extraordinary amounts of kinetic energy. But when that energy is released instantaneously upon impact, when the rock hits the surface and stops, the result is an explosion. The rock vaporizes. The ground beneath it vaporizes. A shockwave propagates outward, excavating a bowl-shaped cavity, ejecting material in all directions, throwing debris on arcing trajectories that can carry it for miles. And for a brief instant, the explosion is bright enough to be visible from space. On average, the moon experiences approximately 7.4 impacts, significant enough to produce a detectable flash per hour. During meteor showers, those periods when Earth and the moon pass through the debris trail of a comet and encounter higher than usual concentrations of space rocks, this rate climbs to approximately 12.6 impacts per hour. The moon is being bombarded, constantly, ceaselessly, by a solar system that has not yet finished clearing itself of the debris left over from its formation 4.6 billion years ago. The crew of Integrity counted 6 flashes. 2 of those occurred during the communication blackout, when the spacecraft was behind the moon and no signal could reach Earth. Those 2 flashes were witnessed by 4 human beings and no one else. No camera captured them, no data downlinked to the ground. They existed as a shared experience of 4 people in a tin can 250,000 miles from home, watching rocks fall on the moon. There is something quietly profound about that. In the entire history of human observation, all the telescopes, all the satellites, all the careful years of cataloging the universe, those 2 flashes were seen only by those 4 people. The universe does things that nobody records. Events happen and unhappen in places no camera watches, at moments no instrument observes. The far side of the moon has been experiencing this all along for 4 billion years, with no witnesses. 4 billion years of rocks falling in absolute darkness and absolute silence and absolute solitude, and the surface recording each one in stone. Now, the blackout. This requires some imagination to really feel. You have been in communication with Earth for 3 days. The voices of mission control have been a constant presence, not always saying much, not always urgent, but always there, a thin thread of connection between yourself and the world you came from. Houston, this is Integrity, all systems nominal. Copy that, Integrity, you're looking good. Simple words, but they carry weight. They mean you are not alone. Yet they mean other humans know where you are. They mean if something goes wrong, someone will know. And then, as Orion moves around the limb of the moon, the thread goes quiet. The moon is large enough, 2,159 miles in diameter, that it physically blocks radio signals. Radio waves travel in straight lines. They cannot bend around the moon. As Orion passes behind the lunar disk from Earth's perspective, the moon interposes itself between the spacecraft and every antenna on Earth, and the signal simply stops. Not degrades, not weakens, stops. The transition happens quickly. One moment there are voices, the next moment there is static, and then the static fades too, and there is nothing. This is called loss of signal, or LOS in the language of spaceflight. Mission Control notes the time and begins counting. And the crew notes the time and continues their work. Everything that needs to happen has been programmed, planned, rehearsed. They know what to do. They know physics will bring them back around. They know the orbital mechanics are reliable in a way that nothing else in human experience is reliable. The kind of reliable that comes from being a consequence of mathematics, rather than human effort or intention. But knowing these things and feeling them are different. The crew of Apollo 8 described the blackout as the most profoundly isolating experience of their lives. Not frightening exactly, not panicked, but a kind of aloneness that had no precedent in their experience. Collins, who orbited alone in the command module while Armstrong and Aldrin were on the surface during Apollo 11, has written about the far side experience with remarkable honesty. He said that while the 3 billion people on Earth and the 2 people on the surface were separated from him by a sheet of rock, he did not feel abandoned or lonely. He felt strong, competent, whole, and yet the silence was different from any other silence. It was not peaceful, not in the ordinary sense. It was the silence of a universe that did not know or care whether he was there. For the crew of Artemis II, this experience was different from Apollo in one crucial way. They were farther, approximately 252,000 miles from Earth, compared to the roughly 239,000 miles of a typical lunar orbit. The maximum distance between a human being and every other human being in history was achieved during their transit. And if you think carefully about what that means, if you imagine a sphere 252,000 miles in radius, centered on their spacecraft, containing the entire human population of the solar system minus 4 people, it begins to feel less like a technical detail and more like a fact about the nature of existence. They were also seeing something that the Apollo crews had seen, but that very few humans in the following decades had been able to experience. Earthset. Earthset is what it sounds like. Just as we on Earth watch the moon rise and set, moving across the sky as Earth rotates, an observer on or near the moon sees Earth rise and set, moving slowly across the lunar sky as the moon moves through its orbit. From the near side of the moon, Earth is always visible, always hanging in approximately the same position in the sky, because the moon is tidally locked. But as you travel around to the far side, Earth sinks toward the horizon. Its reflected light fades, and then it disappears, and you are in a sky without Earth for the first time in the history of your species. Commander Wiseman said later that watching Earthset was not something he had prepared himself to feel. He knew it would happen. He had trained for the blackout, had studied the orbital mechanics, had practiced the procedures for the far side transit 100 times in simulation. But the actual experience of watching his planet disappear behind the lunar horizon was different from any training. He described it as watching a light go out, a specific, familiar light that had never gone out before. Now let us go to the far side itself. At the moment Orion rounded the limb and the far side came into view, the crew fell quiet. They had been briefed on what to expect. They had studied photographs from orbiters, the Lunar Reconnaissance Orbiter, China's Chang'e probes, Japan's Kaguya spacecraft, a decade of high-resolution orbital imaging. They knew, in their minds, what the far side looked like. They knew it was different from the near side. They knew it was rougher, more heavily cratered, largely lacking in volcanic plains. None of that preparation quite captured the reality. The far side of the moon, seen with human eyes from close orbital distance, looks like the end of something, like a record of every violent thing that ever happened in the early solar system, all of it preserved in stone, none of it healed. As the near side has that patchwork quality, dark plains and bright highlands, smooth and rough alternating, a landscape with some visual rhythm to it. The far side is almost entirely one thing. Cratered highlands, as far as you can see, in every direction. Crater within crater within crater. Ancient impacts overprinted by newer ones. The whole surface, a palimpsest of catastrophe. Layer upon layer of violence, going back 4 billion years. The largest feature on the far side, and indeed, one of the largest impact structures anywhere in the solar system, is the South Pole Aitken Basin. It is approximately 1,550 miles in diameter and up to 5 miles deep. To put that in perspective, the United States from East Coast to West Coast is roughly 2,800 miles across. The South Pole Aitken Basin is more than half that width. And it is so large that if you were standing at its center, you would not be able to see the rim from any direction. The moon's curvature would hide it below the horizon. You would not even know you were inside an impact basin unless someone told you. This basin was formed approximately 4 billion years ago, during a period that geologists and planetary scientists call the Late Heavy Bombardment, when the solar system was a far more violent place than it is today, when the giant planets were still settling into their current orbits and their gravitational jostling was flinging enormous numbers of asteroids and comets into the inner solar system. The object that created the South Pole Aitken Basin was likely hundreds of miles in diameter, traveling at tens of kilometers per second. And it struck the moon with an energy release that is essentially impossible to contextualize in human terms. The impact excavated material from deep in the moon's interior, revealing rocks that formed in the lunar mantle. Rocks that had never been exposed on the surface before, and that carry information about conditions inside the moon billions of years ago. This basin is scientifically one of the most valuable places in the solar system, and humanity has never sent a spacecraft to study it from the surface. The Chinese Chang'e 4 lander, which arrived in January 2019, the first spacecraft ever to land on the far side of the moon, touched down in a smaller crater within the South Pole Aitken Basin called Von Karman. And what it found there confirmed and deepened the mystery of why the two hemispheres of the moon are so different. But the crew of Integrity, orbiting overhead, was seeing something that no photograph conveys: the sheer scale of it. The sense, which you can get from orbit in a way you cannot get from a flat image, that the surface below you is not just cratered, but fundamentally, deeply, structurally cratered. That the crust itself has been repeatedly shattered and reformed and shattered again until what you are looking at is not so much a landscape as a geological record. One of the crew members, historical accounts suggest it was Christina Koch, described the far side as looking broken. Not merely rough or cratered, but broken in the way that something is broken when it has been hit so many times that its original form is no longer recoverable. The near side of the moon, despite its age, has a certain coherence. The large volcanic plains give it a structural identity, regions of smooth, dark stone that stand in visual contrast to the highlands and give the face we know its distinctive character. The far side has no such anchor. It is highlands all the way to the horizon, in every direction, cratered and recurved and fractured and ancient. This difference, the dramatic asymmetry between the two hemispheres, is one of the central puzzles of lunar science, and it has occupied researchers since the first photographs from Soviet orbiters in the 1960s revealed the far side's character. Over the following decades, several hypotheses emerged. The most widely discussed involves the distribution of a specific type of rock called creep, an acronym for potassium, rare earth elements, and phosphorus. These elements are found in a particular type of volcanic rock called basalt, and they are concentrated almost entirely on the near side of the moon. Creep basalt forms when magma with a high concentration of heat-producing radioactive elements cools. The radioactive elements generate heat, which keeps the surrounding rock warm, which allows volcanic activity to continue long after it would otherwise stop. If creep is concentrated on the near side, it means the near side has had access to more internal heat for longer, which means more volcanic eruptions, which means more lava flooding the ancient impact basins and smoothing them out into the flat plains we see as Maria. The question is why creep is concentrated on the near side. Why would the moon's radioactive elements preferentially end up in one hemisphere? The answer, and according to the leading hypothesis, goes back to the very beginning of the moon, and it involves a magma ocean. When the moon formed, most likely from the debris thrown out by a catastrophic collision between the early Earth and a Mars-sized protoplanet called Theia, it was initially molten, a global magma ocean, possibly hundreds of miles deep, covering the entire young moon. As this ocean cooled and solidified over tens of millions of years, different minerals crystallized out of the magma at different times and sank or floated at different rates, in a process called magmatic differentiation. The heavier minerals sank, the lighter ones floated, and eventually a solid crust formed at the top. But here is the key. The crystallization of this magma ocean was not symmetric. The near side of the moon, facing the early Earth, would have cooled differently from the far side, which faced open space. Some researchers believe that this asymmetry in cooling led to an asymmetry in the final distribution of minerals, with creep-bearing materials concentrated near the thinner crust of the near side, where volcanic activity could later bring them to the surface. More recent work has added another layer to this story. Computer simulations suggest that the impact of Theia itself may have been asymmetric, that the force of the collision preferentially heated one hemisphere of the forming moon, driving convection patterns that concentrated the incompatible elements, including creep components, into a roughly Earth-facing hemisphere. The asymmetry in this model was built into the moon from the moment of its birth, as the crew of Integrity was flying over the physical evidence of this 4-billion-year-old event. The cratered highlands below them were not merely old, they were ancient in a specific way, preserved in their original state because they never experienced the volcanic flooding that would have buried them under lava. The far side is a window into the early solar system in a way that the near side is not, because it never had the geological activity that would have erased that record. Let us talk about water, because one of the most important scientific results of recent years, and one directly relevant to any future human presence on the moon, involves water ice, and the far side has something important to say about it. We now know that the moon has water, not liquid water on the surface, not an ancient ocean or a buried lake, but water ice, preserved in permanently shadowed craters near the poles. The floors of certain polar craters never receive sunlight. The geometry of the moon's axial tilt and the steepness of the crater walls mean that the deepest parts of these craters are in perpetual shadow, with temperatures that can drop below -300 degrees Fahrenheit. At those temperatures, water ice deposited by comets and asteroids over billions of years is stable. It does not evaporate. It sits there, locked in the cold dark, waiting. This ice is potentially of enormous value for human exploration. Water can be used for drinking, for growing food, and, critically, for making rocket fuel. Water molecules, broken apart by electrolysis into hydrogen and oxygen, provide the two components of the most efficient chemical rocket propellant available. A base at the lunar pole with access to water ice would be essentially self-sustaining in terms of propellant, which dramatically changes the economics and practicality of long-term lunar operations and further down the road missions to Mars. But the far side complicates this picture in an interesting way. Data from the Chang'e 6 mission, China's landmark far-side sample return mission that successfully brought back material from the Apollo crater within the South Pole Aitken Basin in 2024, revealed something unexpected. The far side contains approximately 100 times less water than the near side. The near side, with its volcanic history and its creep-rich basalts, has water locked in the volcanic glass beads produced by ancient eruptions. The far side's ancient highlands preserve almost no such water. This means that the water resources of the moon are not uniformly distributed. The places where human bases might most naturally be built, near the poles with access to solar power, and to the permanently shadowed craters that contain water ice, are not equally distributed between the near and far side. The practical implication is that future lunar bases will almost certainly be concentrated at the near side poles, particularly in the South Polar region, where much of the confirmed water ice is located, and that the far side, for all its scientific value, poses additional logistical challenges for human habitation. For the crew of Artemis II, this was not an abstract policy question. They were the first humans to personally observe the far side from close quarters, and in what they were seeing was relevant to every future mission that might follow. Every scientific result, every observation, every data point they collected would feed into the planning for Artemis III and beyond, the missions that would, eventually, put humans back on the lunar surface for the first time since 1972. There is a moment in the transit of the far side that is, by all accounts, one of the most powerful experiences of the entire mission. It happens as the spacecraft comes around the far side and Earth comes back into view. It is called, by obvious analogy, Earthrise, or, from the crew's perspective, the end of Earthset. The planet reappears at the lunar horizon, a blue-white sphere hanging in the blackness of space, looking improbably small and improbably beautiful. Now, the original Earthrise photograph, taken by Bill Anders during Apollo 8 on Christmas Eve 1968, is one of the most reproduced and most emotionally resonant images in human history. It is often credited with catalyzing the modern environmental movement, with giving people a visual vocabulary for the idea that Earth is finite and fragile and precious. It showed the planet not as the infinite, permanent backdrop of all human experience, but as an object, a specific, bounded, vulnerable thing floating in space. But a photograph is not the experience. The crew of Artemis II, watching Earth reappear after 40 minutes of blackout, were not looking at a photograph. They were looking at the real thing. And the emotional weight of the moment, coming on the heels of the isolation and the silence and the strange beauty of the far side, was, according to subsequent accounts, almost overwhelming. Commander Wiseman has spoken about this moment in terms that echo what astronauts across several generations have struggled to articulate: the overview effect. This is the name given to the cognitive and emotional shift that astronauts report experiencing when they see Earth from space. It is not a single feeling, but a cluster of them. A sudden, visceral sense of the smallness of national borders and geopolitical conflicts, a feeling of connection to all of humanity as a single species on a single world, a deep and somewhat frightening awareness of how thin the biosphere is, how fragile the conditions for life, how different the reality of the universe is from the reality of daily human experience. The overview effect is not universal. Not every astronaut reports it, or reports it in the same way. But it is common enough and described with enough consistency across cultures and time periods that researchers have begun studying it seriously, asking what it is, physiologically and psychologically, and whether it can be replicated or induced without the experience of spaceflight. What seems to happen at the neurological level is something like this. The brain holds a model of the world. This model has been built over an entire lifetime of sensory experience, and it is deeply embedded, deeply reliable, deeply resistant to revision. The model says, among other things, that Earth is large, that it extends to the horizon in every direction, that it is solid underfoot and the sky is above, and everything familiar is within reach. Yet this model is so fundamental that it feels less like a belief and more like a perception. And then you float to the window of a spacecraft and look out, and the model is wrong. Earth is not large. It is a sphere, a finite sphere, and you can see the whole thing at once, and your thumb at arm's length can cover it. The model has to update. And because the model has been wrong about something so fundamental, because reality is so different from what the embedded representation predicted, the update is not just intellectual, it is emotional, it is physical, it shakes something loose. The crew of Integrity had this experience watching their planet reappear after the blackout. The relief of seeing it, the beauty of it against the black, the awareness of how much it meant. Not as an abstract symbol, but as a specific, irreplaceable place containing everyone they loved, produced something that Commander Wiseman, trying to describe it afterward, said was not quite like any emotion he had ever felt before. Not joy exactly. Not sadness. Something between gratitude and awe, with a note of fear underneath. Fear of what? Perhaps of distance. Of the reality that they were here, and everyone else was there, and the between was just space. Just nothing, just vacuum. Just the dark that holds everything and cares about none of it. Let us now go deeper into the science of the far side, because the science is not dry. The science is, in many ways, the most astonishing part of the story. The crust of the far side of the moon is thicker than the crust of the near side by approximately 20 kilometers. This might not sound significant in everyday terms. 20 kilometers is about 12 miles. But in planetary science terms, it is enormous. The crust is the outermost solid layer of a world, the part that records its history, the part that determines what kinds of volcanic and tectonic processes are possible. A 20-kilometer difference in average crustal thickness between two hemispheres of the same object is a profound structural asymmetry. Why is the far side's crust thicker? The leading explanation connects back to the magma ocean cooling scenario we discussed earlier. If the near side cooled more slowly, perhaps because of tidal heating from the early Earth, or because of the higher concentration of radioactive creep elements generating heat from within, then the crust on the near side would have taken longer to solidify and would have ended up thinner, leaving more of the interior accessible to later volcanic activity. The far side, cooling faster, developed a thicker, more rigid crust that was harder for magma to push through from below. This has a direct consequence. The volcanic maria that characterized the near side required magma to reach the surface from the interior. On the near side, the thinner crust allowed this relatively easily. On the far side, the thicker crust formed a barrier. Most magma simply didn't have enough pressure behind it to push through 20 extra kilometers of solid rock, and it stalled in the interior, never reaching the surface, leaving the far side's ancient cratered highlands intact and unmodified. There is one exception: the Aitken Basin, which actually straddles the boundary between the near and far sides and is visible from Earth as a small, barely resolved feature, shows some volcanic fill. A reminder that even the far side was not completely immune to volcanism, only much less susceptible to it. But the general rule holds. The thick crust of the far side is the reason it looks the way it does, and the thick crust is a consequence of asymmetric cooling that began 4 billion years ago. The crew of Integrity was flying over the evidence of all of this, over the preserved record of the moon's birth and early history. Under their spacecraft was rock that had not been touched by volcanic activity for 4 billion years. And under their spacecraft was a surface that had been accumulating impact craters since the solar system was young, building up layer upon layer of smashed and melted and re-solidified material, a geological record of violence that is available nowhere else in the inner solar system in such complete and ancient form. On Earth, the geological record only goes back about 4 billion years, and even that early record is fragmentary and scrambled by the relentless geological activity of a living planet. Plate tectonics, erosion, volcanism, subduction, all the processes that continuously reshape the surface and destroy old rocks and produce new ones. The moon has none of this. The moon stopped being geologically active in the deep interior sense billions of years ago. Its surface is a fossil, and the far side is the most fossil-like part of it. The oldest, least modified terrain in the entire solar system, accessible to spacecraft. Scientists dream of sending a human geological team to the far side highlands. The ability to walk over terrain, to pick up rocks and examine them in context, to notice the subtle relationships between different rock types that a camera cannot capture, to drill cores and extract sequences of material from different depths. This would tell us things about the early solar system that no orbital survey can provide. But getting humans to the far side presents a specific challenge that has no equivalent anywhere else in the solar system: communication. On the near side, astronauts can communicate directly with Earth. On the far side, the moon itself blocks all direct communication. So any future crewed landing on the far side will require a relay satellite, a spacecraft in an orbit that gives it line of sight to both the lunar far side and to Earth simultaneously, acting as a communication bridge. China has deployed such a relay satellite, Quikiao, specifically to support Chang'e 4 and subsequent far-side missions. Future crewed far-side missions will require more robust relay infrastructure, the Terminator. This word, which has acquired a different set of associations through science fiction, means something specific and beautiful in the context of the moon. The Terminator is the line between the sunlit and the shadowed parts of the lunar surface, the boundary between day and night on the moon. And from orbit, it is one of the most scientifically revealing features you can observe on Earth. And the Terminator is not particularly dramatic. We have an atmosphere, and the atmosphere scatters light, creating the gradual transitions of dawn and dusk, softening the boundary between day and night into something gentle and diffuse. The moon has no atmosphere, so the Terminator is sharp, not perfectly sharp. A Terminator is a geometric line, not a physical one, and the surface it crosses is not perfectly flat, but sharp enough that shadows near it are long and precise and dramatic. When the sun is low near the horizon of a particular point on the lunar surface, when that point is near the Terminator, the shadows cast by every crater rim, every boulder, every ridge and escarpment are enormously elongated. Small features that would be invisible or nearly invisible under direct overhead sunlight become starkly evident, yet their shapes thrown into high relief by the low-angle illumination. It is as if someone is holding a flashlight at the ground, at a very low angle, raking the light across the surface, making every tiny irregularity visible as a shadow. For the crew of Integrity, watching the Terminator cross the far side was an experience of seeing the moon in a completely different way from anything that photographs had prepared them for. Features that appeared in orbital images as simple, undifferentiated terrain suddenly revealed hidden complexity. Subtle ridges, gentle valleys, the remnant rims of craters so old and so eroded that they had become nearly invisible under direct illumination, brought back into visibility by the raking shadows of the Terminator. One astronaut's account described the experience as seeing a completely different world. And not a world that was unfamiliar in a frightening way, but unfamiliar in the way that a familiar face looks different under unusual light. The same features, the same underlying structure, but emphasized differently, organized differently, made strange by the change in angle. Things that had been invisible became visible. Things that had seemed significant receded. The terrain rearranged its hierarchy of importance according to the logic of the light. This has practical scientific implications. Some of the most important geological features of the moon, the subtle scarps that indicate ancient contraction as the interior cooled and shrank, the gentle ridges that mark the edges of ancient lava flows, the barely visible ghost craters that are mostly buried under later deposits, are most visible near the Terminator. Scientists studying the moon's geological history carefully time their observations to correspond with specific lighting conditions, looking at the same feature from different sun angles to build up a complete picture of its three-dimensional form. But the Terminator is also beautiful. The crew of Integrity watched it track across the far side, the line of shadow advancing as the moon rotated relative to the sun. And what they saw was a landscape being revealed and concealed in slow motion, a surface that changed character as the light changed, a world that was not one thing but many things, depending on where the light was coming from. Now let us talk about something that exists at the intersection of science and strangeness: the lunar swirls. These are one of the most mysterious features of the moon's surface, and they are particularly associated with the far side. A lunar swirl is exactly what it sounds like: a bright, swirling pattern on the lunar surface, visible from orbit as a lighter-colored region with a distinctive curved or spiral shape. They range in scale from small features a few miles across to enormous structures hundreds of miles wide. The largest and best known, called Reiner Gamma, is on the near side, a beautiful, intricate swirl shape clearly visible in telescopic images. But many of the most prominent swirls are on the far side, and their distribution is not random. Lunar swirls always occur where there are strong local magnetic anomalies. The moon, unlike Earth, does not have a global magnetic field. Earth's field is generated by the dynamo action of its liquid iron outer core, and it extends thousands of miles into space, shielding the planet from the solar wind, a continuous stream of charged particles flowing outward from the sun. The moon's interior is too small and too cool to generate such a field, and so the moon is, overall, exposed to the solar wind without protection. But locally, in specific, limited regions, the moon has strong magnetic fields, not generated by an active dynamo but preserved in the rock from a period billions of years ago when the moon did have a global magnetic field. Exactly when and why the moon once had a magnetic field and why it lost it is still debated. But the remnant magnetism locked into ancient rocks in certain regions is real and measurable, and it has an interesting effect on the solar wind. Where the local magnetic field is strong enough, and it deflects the solar wind particles that would otherwise constantly bombard and alter the surface. The solar wind does not just shine on the moon, it actively changes it. Charged particles hitting the surface over billions of years cause chemical changes in the topmost layer of minerals, gradually darkening and reddening the surface through a process called space weathering. Regions shielded from the solar wind by local magnetic fields experience less space weathering, and so they remain brighter, more reflective, lighter in color. The swirling shape of the features is thought to reflect the swirling geometry of the magnetic field lines. The pattern of protection against the solar wind is not a simple circle or rectangle, but a complex, curved shape determined by the specific configuration of the magnetized rock below. What caused the ancient magnetization in the first place? This is where the theories get interesting. One possibility is that large impact events, the same impacts that created the moon's large basins, generated enough heat and pressure to magnetize rock in specific configurations as the shock waves propagated through the crust. Another possibility involves ancient magma that cooled in the presence of the moon's early magnetic field, freezing the field's orientation into the rock like a compass needle frozen in mid-swing. The crew of Integrity, passing over the far side's magnetic anomalies, could not see the magnetic fields directly, of course. But the instruments aboard Orion were recording them. The magnetometer data from the far side transit will provide valuable information about the distribution and strength of these remnant fields, data that will be used to refine models of the moon's early magnetic history. And the swirls themselves, visible as pale, curved patterns against the darker surrounding terrain, were visible through the windows, not the most dramatic visual feature of the far side. The craters, the basins, the vast cratered highlands all compete for attention, but among the strangest, because they are features that have no clear analog in everyday experience. Swirling patterns on a rock surface, created by invisible magnetic fields protecting patches of ground from the constant bombardment of charged particles from the sun. Ancient magnetic tattoos recording a field that no longer exists, preserved because the moon is geologically dead and has no mechanism to erase them. Let us talk about cosmic rays. Because the crew of Integrity, during their journey around the moon and beyond, experienced something that no person on Earth ever experiences: the feeling of being outside the protection of Earth's magnetic field. Earth's magnetic field does not merely deflect the solar wind. It deflects a much more energetic class of particles, cosmic rays. These are not rays in the light sense. They are high-energy charged particles, protons and atomic nuclei, accelerated to enormous velocities by supernovae and other violent astrophysical events. When they hit Earth's magnetic field, the field curves their path, sending them spiraling along field lines and eventually funneling them toward the poles, where they interact with the atmosphere to produce auroras. But very few cosmic rays penetrate to Earth's surface. The atmosphere provides additional shielding, slowing and absorbing the particles that do make it through the magnetic barrier. In space, outside the magnetosphere, outside the atmosphere, cosmic rays are everywhere and constant. They pass through the hulls of spacecraft, through clothing, through the walls of biological cells, through DNA, depositing their energy in ways that can damage the molecular machinery of life. Astronauts in low Earth orbit, on the International Space Station for instance, are partially protected by Earth's magnetic field, which extends several thousand miles into space. But beyond a certain distance, the protection drops dramatically. Astronauts traveling to the moon, and especially around the moon's far side, are in interplanetary space, exposed to the full flux of cosmic radiation, with only the relatively thin walls of their spacecraft for protection. The result of this exposure, for many astronauts, is visible. Literally. Cosmic ray particles passing through the fluid-filled eyeball can produce light flashes, brief streaks or spots of light perceived even with eyes closed, in total darkness. This phenomenon was first reported by Apollo astronauts, who described seeing flashes of light while resting in the darkened cabin of their spacecraft, and it has been studied extensively since then. Yet the leading explanation is that the cosmic ray particles interact with the vitreous humor, the gel-like interior of the eye, or with the retina directly, triggering the same kind of signal that would be produced by actual light. The retina reports a photon when there was no photon because the particle's passage through the photoreceptors mimics the photoelectric effect of real light. The crew of Artemis II reported these flashes. Multiple crew members described seeing them, particularly during the periods of higher radiation exposure around the far side transit. The experience is described as harmless in the short term. The flashes are brief and occasional, not continuous, and they cause no visual impairment. But the underlying radiation exposure is not harmless in the long term. Every cosmic ray passing through the body deposits a small dose of ionizing radiation, and ionizing radiation is one of the primary risk factors for cancer in astronauts on long-duration missions. Managing radiation exposure is one of the central challenges of deep space exploration, and it is a challenge that gets dramatically harder beyond low Earth orbit. The Apollo astronauts were exposed to radiation levels significantly higher than those experienced by ISS crew members, and the consequences of that exposure are still being studied. The crew of Artemis II, spending more time in deep space on a longer, more distant trajectory than any Apollo mission, will have accumulated a radiation dose that will be carefully monitored for the rest of their lives. There is something philosophically interesting about the cosmic ray flashes that the crew saw. Every flash was a particle from somewhere else in the galaxy, a proton or an iron nucleus accelerated to near light speed by a supernova explosion, perhaps thousands of light years away, traveling through the vacuum of interstellar space for millions of years, entering the solar system, and happening to intersect the trajectory of a small spacecraft carrying 4 human beings around the moon, and announcing its arrival by triggering a ghost of light in someone's eye. The universe reached in and touched them. Not metaphorically, physically. Particles that were once inside a star, scattered by that star's explosion, had traveled unimaginable distances in unimaginable time and found their way to this specific place at this specific moment and passed through 4 human bodies, leaving traces in DNA and images in eyes, connecting these 4 people to a cosmic history that has been unfolding since long before the Earth existed. At some point during the far side transit, Commander Wiseman gathered the crew's attention toward a pair of craters that appeared in the orbital photographs they were using to navigate and document the surface. These were small craters, unnamed, unremarkable from a purely scientific standpoint. The naming of lunar features is governed by the International Astronomical Union, and there are formal procedures for submitting names and having them ratified. Typically, names are proposed by scientists studying specific features, and they follow established conventions. Most craters are named after scientists, mathematicians, artists, and explorers. But there is some informal precedent for field naming, for the kind of spontaneous naming that occurs when a person is physically present at a place and a name presents itself naturally. Commander Wiseman had lost his wife, Carol, to cancer in 2020. She died while he was in the middle of his career as an astronaut, in the years between his first and second space flights. He had raised their daughters alone, continued his training, continued his preparation, and been selected for the most ambitious human spaceflight mission in 50 years. He carried her with him, as such losses are carried, not always consciously, but present in the weight of daily life, in the meaning attached to accomplishment, out in the quiet internal dedication of effort. Looking down at 2 unnamed craters on the far side of the moon, 250,000 miles from Earth, in a place no human had ever been before. He named one of them Carol. What happened in the capsule at that moment? The reaction of the crew, the brief silence, the hug that followed in the microgravity of the spacecraft, has been described by those who witnessed it as one of the most profoundly human moments of the entire mission. The universe is vast and indifferent. The moon is violent and ancient and does not care. But 4 human beings floating in space, one of them with a heart full of grief and love, named a small piece of it for someone who is gone. There is a category of human experience that resists reduction to data. The grief of loss is one of them. The love that survives grief is another. Yet the impulse to mark places with names, to inscribe the personal into the indifferent geology of the universe, is one of the oldest things human beings do. We have been naming hills and rivers and stars since before we had writing to record the names. Commander Wiseman, naming a crater for Carol, was doing something that his species has always done, making meaning in a universe that offers no meaning of its own. Mission Control, receiving the transmission with a 1.3-second delay, went silent for a long moment. Then they acknowledged. Copy that. Integrity. Carol Crater. Outstanding. Let us step back now from the specific mission and think about what the moon means as a scientific object, what it has already told us, and what it still has to tell us. The moon is, in a sense, the moon. It's the most important object in the solar system for understanding Earth's history, not because the moon and Earth are similar, in many ways they are dramatically different, but because the moon is a record, a fossil, a preserved witness to the early solar system that Earth, with its dynamic geology and relentless recycling, cannot provide. Consider the late heavy bombardment. That period, roughly 3.8 to 4.1 billion years ago, when the inner solar system experienced a concentrated pulse of large impacts. The evidence for this event is preserved on the Moon in the enormous impact basins, the Imbrium Basin, the Oriental Basin, the Serenitatis Basin, all of which formed during this period and are visible as the dark circular Maria on the near side, or as structural features on the far side. These same impacts would have struck Earth too. But Earth's active geology has erased most of the evidence. The Moon kept the record that Earth lost. The late heavy bombardment matters for life on Earth because it was occurring at roughly the same time that life first appeared. If the geological record of the Moon tells us that the bombardment was intense and extended, then it implies that life on Earth either survived this bombardment, sheltering in deep ocean hydrothermal vents or subsurface environments, or arose astonishingly quickly in the brief window between major impacts. If the bombardment was shorter and less intense than previously believed, then life may have had more time to get established than we thought. The far side of the Moon is particularly important for this kind of research because its ancient terrain has been less modified by subsequent volcanism. The far side highlands preserve the original impact record in more complete form than the near side, where volcanic flooding has buried and obscured many of the oldest impact structures. What else does the Moon record? The history of the solar wind is one answer. The topsoil of the Moon, called the regolith, is a layer of broken, powdery material created by billions of years of meteoroid impacts, grinding the surface rock into fine fragments. This regolith contains a record of the solar wind going back billions of years. Atoms implanted in the surface grains by the constant bombardment of solar particles. Apollo astronauts brought back samples of regolith that have been studied for 50 years. And the solar wind record preserved in them has helped scientists understand how the sun has changed over its lifetime. The Moon also records the history of supernovae. When a star near the sun explodes, it sends a wave of high-energy particles outward. Some of these particles are iron-60, a radioactive isotope produced only in supernovae and nowhere else. Iron-60 has been found in lunar regolith samples and in deep-sea sediments on Earth, and by dating these deposits, scientists have been able to identify specific periods of relatively nearby supernova activity in our cosmic neighborhood over the last few billion years. The Moon is not just a geological object, it is an archive. A record of the solar system's history kept in stone and dust, waiting to be read by anyone patient and curious enough to make the journey. The far side also has implications for radio astronomy that are only beginning to be explored. Radio astronomy is the observation of the universe through radio waves, the very long wavelength end of the electromagnetic spectrum. Radio waves from space can tell us things about objects and events that visible light cannot reveal. The hydrogen clouds between the galaxies, the remnants of supernova explosions, the radiation emitted by pulsars, the cosmic microwave background, the faint afterglow of the Big Bang that still permeates the universe like the residual warmth of an ancient fire. Radio astronomy on Earth has one fundamental limitation: radio frequency interference. Every cell phone tower, every Wi-Fi router, every television broadcast, every microwave oven emits radio waves, and these human-generated emissions fill the radio spectrum in and around populated areas, and making it difficult or impossible to detect the faint radio signals from astronomical sources. Astronomers build their radio telescopes in remote, isolated locations, desert valleys, high plateaus, and work constantly to exclude interference. But they cannot escape it entirely. The sky above Earth is full of human radio noise. The far side of the Moon, shielded from Earth by approximately 2,000 miles of rock, would be the quietest radio environment reachable by humans, or by human-built instruments. A radio telescope on the lunar far side would have no terrestrial interference whatsoever. How, in a frequency range below 30 megahertz, the decameter wavelengths that are blocked by Earth's ionosphere, and therefore completely inaccessible to ground-based observatories. A far-side telescope could observe the universe with sensitivity and clarity, unavailable anywhere on or near Earth. The 21-centimeter hydrogen line which traces the distribution of neutral hydrogen throughout the universe and can potentially reveal the structure of the universe in the cosmic dark ages before the first stars formed, could be observed with unprecedented precision from a far-side radio array. This is not a speculative, distant possibility. The scientific community has been discussing lunar far-side radio astronomy for decades, and the first steps toward it are already being taken. China's Chang'e 4 mission carried a small radio astronomy experiment. NASA is funding studies for a concept called the Lunar Crater Radio Telescope, which would use a natural crater on the far side as the reflective dish of an enormous radio telescope, essentially filling a 2-mile-wide crater with a wire mesh reflector to create a telescope larger than any that could be built from scratch. The far side of the moon, in this vision, is not just a place to study, but a place from which to study. A natural observatory platform, shielded from radio noise, offering a window into the universe that has been closed to us by the noise of our own civilization. The crew of Integrity was aware of all of this. They were not merely touring a scenic landscape. They were scouting a future research platform, observing a world that will play a central role in humanity's scientific future, yet carrying the eyes and the minds of a species that is only beginning to understand what it has next door. Now let us go back to the meteorites because they deserve more attention than we have given them so far. The 6 impact flashes that the crew observed were not unique events. They were typical of what the moon experiences on any given day. The moon is bombarded continuously, at a rate that has varied over the history of the solar system but has never stopped. The current impact rate is dramatically lower than it was during the late heavy bombardment 4 billion years ago, but it is still significant. Spacecraft in lunar orbit have been instrumented to count impacts, and the data they have returned suggests a rate of bombardment that is higher than many people realize. The practical implications of this for future lunar infrastructure are serious. A crater large enough to threaten a structure with direct impact, say tens of meters across, is rare. But micrometeorites, particles too small to produce a visible flash but moving at full cosmic speeds, bombard the surface constantly. They gradually erode surfaces, sandblasting material at the molecular level, degrading solar panels, pitting windows, wearing down the surfaces of structures exposed to the lunar environment. There is also the issue of ejecta. When a meteoroid strikes the moon, it excavates a crater and throws material outward, fragments of rock, particles of powdered regolith, droplets of melted glass, on ballistic trajectories. Some of this material travels for miles. And a habitat on the lunar surface is not just threatened by direct meteoroid impact, it is threatened by the ejecta from impacts in the surrounding area. A meteoroid striking a kilometer away can send material flying across the surface that could damage a structure, could pit a viewport, could degrade a spacesuit. The Apollo astronauts who walked on the lunar surface came back with spacesuits that were visibly worn. The lunar dust, the fine-grained regolith that covers the surface like a layer of powdery talc, had worked its way into every mechanism, scratched every glass surface, abraded every fabric. Lunar dust is not like Earth dust. It has never been rounded by water or wind. Every particle is jagged, irregular, with sharp edges that catch and hold, that abrade surfaces that penetrate lungs if inhaled. It is one of the most significant engineering challenges facing lunar surface operations, and it is a direct consequence of the moon's violent bombardment history. The regolith is made of smashed rock, and smashed rock is sharp. None of this makes lunar exploration impossible. It makes it harder, more demanding of careful engineering, more expensive, but it is worth being clear-eyed about. The moon is not a gentle or forgiving environment. It is a place where the universe's violence is on full display, unmediated by any of the protective systems that make Earth habitable. The crew of Integrity was seeing this directly. The impact flashes they watched were reminders that the same forces that shaped the geological record they were studying were still active, still operating, still posing a threat to any structure placed on that surface. Now let us talk about the giant impact basins one more time because they deserve more attention, particularly the Aitken Basin, which the crew of Integrity observed on the far side limb. The Aitken Basin is a masterpiece of geological violence. Roughly 600 miles in diameter, It is one of the best preserved large impact basins in the solar system, and what makes it particularly special, and particularly beautiful, is its concentric ring structure. When a very large impact occurs, the shock wave propagates outward through the crust, and if the impactor is large enough and the crustal material has the right properties, the crust can respond by forming a series of concentric rings around the impact point, like ripples in a pond but frozen in stone. Orientale has 3 main rings, nested within each other, visible from orbit as arcs of elevated terrain surrounding the central basin. These ring structures are called multi-ring basins, and they are found throughout the solar system on the larger solid bodies: the Moon, Mars, Mercury, some of the outer planet moons. Their formation is not fully understood. The exact mechanism by which a circular shock wave produces elevated rings rather than a simple bowl is still debated. But Orientale, being relatively fresh, only about 3.8 billion years old, young by lunar standards, and relatively well preserved, it formed after the period of most intense bombardment, so it has not been as extensively overprinted by later impacts, offers the clearest view of this process anywhere accessible to current spacecraft. As the central depression of Orientale is partially filled with mare basalt, one of the few volcanic deposits on the far side, squeezed through the crust by the magma that accumulated at depth. After the impact, thinned the crust. The surrounding rings create a staircase of elevated terrain, each ring tens of miles wide and hundreds to thousands of feet high, giving the entire structure a grandeur that is apparent even from orbital altitude. There is a larger basin on the far side, the South Pole Aitken Basin, which we mentioned earlier. It is larger than Orientale in every dimension, but because it is so much older, it has been so extensively cratered and modified that its ring structure is barely recognizable. The far side is, in many ways, the most ancient landscape accessible to human observation, and an Orientale is one of the youngest features in that ancient landscape, a relative newcomer, formed at the tail end of the period of heavy bombardment. The crew of Integrity passed over both of these features during their transit, and the contrast between them, the fresh, ring-structured Orientale versus the ancient, battered, barely visible South Pole Aitken, is a kind of lesson in geological time. Orientale shows what a large impact looks like before billions of years of subsequent bombardment have worn away the evidence. The South Pole Aitken Basin shows what remains after those billions of years have done their work. A hint, a suggestion, an enormous depression that you might not even recognize as an impact structure if you didn't already know what to look for. One of the things the crew of Integrity observed during their far-side transit that has generated the most scientific discussion is something that falls under the category of color variation in the highlands. The far-side highlands are not uniformly gray. Under the conditions of natural lighting from orbit, not the heavily processed, contrast-enhanced images that are typically used for public release, the surface shows subtle but real variations in color. Some regions have a slightly redder tint, others a slightly greener or bluer one. These variations are not dramatic, but they are visible to the human eye and they are scientifically meaningful. The color of a rock on the lunar surface is a proxy for its composition. Rocks rich in iron and titanium tend to be darker and bluer. Rocks rich in aluminum and calcium, the anorthosites that make up much of the ancient lunar crust, tend to be whiter. Rocks that have been heavily space-weathered tend to be darker and redder than fresh material. By mapping the color variations across the surface, scientists can infer something about the composition and history of different regions. The crew of Integrity was not just sightseeing, they were making observations that could not be replicated by instruments. The human visual system is, in certain specific ways, better at detecting and discriminating subtle color variations than current orbital camera systems. This is partly a matter of spectral sensitivity. The human eye's 3 types of cone cells are tuned to specific wavelength ranges in a way that often detects subtle color differences that single wavelength cameras miss. And partly a matter of neural processing. The brain's visual cortex integrates information from across the visual field in ways that allow it to detect pattern and variation that simple pixel counting algorithms miss. The specific observations made by the crew, the notes they took, the verbal descriptions they recorded, the locations they flagged for follow-up study, will be cross-referenced with orbital imagery and with the suite of instruments aboard Orion to produce a set of scientific results that will take years to fully analyze. This is the nature of scientific exploration. The observations come first. The understanding follows. There is a philosophical dimension to the far side that has been with us throughout this story, and that I want to address directly, now that we are deep enough into the science and the human experience to approach it properly. The far side of the moon represents, in a specific and irreducible way, the unknown. Not the unknown in the sense of being genuinely mysterious. We have mapped it thoroughly, photographed it from orbit, even landed a spacecraft on it. But the unknown in the experiential sense, the side that no one on Earth can see, the side that generations of human beings have lived and died never knowing existed, because the geometry of the moon's orbit simply never showed it to them. Every human culture that has ever existed, in every part of the world, has looked up at the moon and seen the same face, the same features, the same patterns that they interpreted as rabbits or women or men or whatever their cultural tradition taught them to see. The moon they saw was always the near side, and the near side was always the same near side, and behind it, always, perpetually, unchangingly behind it, was a face that no human eye would ever see from the ground. There is something about this that touches the deep human fascination with the hidden and the secret. The moon is our constant companion, so familiar that it has become almost invisible. We stop seeing it the way we stop seeing a painting that has hung on the wall for years. And yet, it has always carried with it this enormous secret, half of itself permanently turned away, permanently hidden, the feature of our sky about which we knew least precisely because it was the most familiar. The first photographs of the far side, sent back by the Soviet Luna 3 probe in 1959, created a sensation that is difficult to fully recapture today. The world wanted to see what was behind the moon, and what was there was not, as science fiction had imagined, not always, alien cities or evidence of intelligent life or some grand cosmic secret. What was there was craters, lots of craters, ancient battered terrain, the same geological material as the near side, but without the volcanic plains, without the features that gave the near side its character. But this was, in its way, more interesting than anything the fictions had imagined. Because what was behind the moon was the solar system's past, the record of creation and destruction, the evidence of a history so violent and so ancient that it takes effort to believe it is real. The far side of the moon is a mirror held up to the early solar system, and what it reflects is a universe that was not built gently. The crew of integrity flying over this terrain were the most recent in a small and distinguished group of human beings who have seen this face directly. Apollo 8, Apollo 10, Apollo 11 through 17, and now Artemis II. A handful of people, in all of human history, who have rounded the lunar limb and found themselves facing a surface that their species never knew existed until 60 years ago. A surface that, for most of human history, was simply the back of the darkness, the unknown made physical, the limit of observation given a shape. Let us take a moment to think about what comes next. Artemis II was a flyby. It did not land. Its purpose was to test the spacecraft and systems in the deep space environment, to confirm that Orion could sustain 4 humans on a long-duration mission beyond low Earth orbit, and to begin the process of extending human presence beyond the small bubble of space closest to Earth. It was, in the language of exploration, a reconnaissance mission, gathering the information and experience necessary to plan what comes after. What comes after, according to NASA's current plans, includes Artemis III, a crewed landing at the lunar South Pole, the first humans on the moon since 1972, the first humans ever to land at the poles, in the vicinity of the permanently shadowed craters where water ice has been confirmed, the first humans to explore the permanently shadowed regions themselves, those deep, cold, and ancient craters where water deposited by comets billions of years ago has been sitting, undisturbed, in a darkness so permanent that the sun has never shined into it in the entire history of the solar system. This is a genuinely different kind of exploration from the Apollo missions. The Apollo landing sites were chosen partly for safety, partly for geological interest, and largely for the spectacular imagery they would provide. The relatively smooth Maria of the near side, familiar from Earth, dramatic from the surface. The polar regions are different. Rougher terrain, extreme lighting conditions, the sun moves near the horizon and never rises high, dramatic temperature variations, and the deep permanent shadows that are scientifically valuable but operationally challenging. But the most significant planned exploration, from a scientific standpoint, is the far side. A crewed landing on the far side of the moon is not part of the immediate Artemis plans. The communication infrastructure required, the relay satellites, the ground stations, the network that would allow continuous contact between a far-side crew and Earth, does not yet exist in sufficient robustness for crewed operations. But the scientific community regards a far-side crewed landing as one of the most important goals of the next phase of lunar exploration. And the observations made by Artemis II, the direct visual observations, the instrument readings, the scientific data collected during the far-side transit, will help make the case and refine the planning for that future mission. When humans eventually stand on the far side of the moon, they will be the first members of our species ever to be in a place where Earth is not in the sky. The first people for whom home is not just far away but literally below the horizon, hidden by a world of rock. The first people who, if they walked to the top of a hill and looked up, would see not the familiar blue-white disk they had known since birth, but only the stars, billions of them, undimmed by atmosphere, in a sky that has never contained Earth. This is the next horizon, not in space, not in light years, but in human experience. The next edge of the known. While we have been following the crew of Integrity around the moon, let us also pause to consider what the moon means for the longer story of space exploration, for Mars, for the outer solar system, for the eventual question of whether humanity is a species that will confine itself to one world or spread across many. The moon is often described as a stepping stone to Mars. This framing is sometimes criticized. Mars is so different from the moon in size and atmosphere and gravity and distance that what you learn on the moon may not directly apply to a Mars mission. But the framing captures something real. The skills and technologies and operational experience required to sustain humans on the lunar surface overlap significantly with what will be required for Mars. The water ice processing that would allow a lunar base to produce its own rocket fuel from local resources is the same basic technology required for in situ resource utilization on Mars. Yes, the radiation management strategies developed for extended lunar stays are the same ones needed for the long Mars transit. The closed-loop life support systems that will sustain astronauts on the moon will need to be reliable enough for the much longer and much more isolated environment of a Mars mission. More fundamentally, the moon provides something that Mars cannot: proximity. A mission to Mars at current technology is a multi-year commitment. A problem encountered on Mars cannot be quickly addressed by sending replacement parts from Earth. The communication delay is up to 24 minutes one way, and a rescue mission is not a viable option in the way that it might plausibly be for lunar operations. The moon, at 3 days travel time and 1.3 seconds of communication delay, yet is close enough to allow for iterative development, for trying things, learning from failures, improving, and trying again, in a way that Mars simply doesn't permit. The history of technology is, largely, a history of iterative development. We did not build the first nuclear reactors by sending scientists to the field with untested equipment. We did not develop the first surgical techniques on the most difficult cases. We learn in relatively safe environments and then apply the lessons to more challenging ones. The moon, for all its hostility, is a relatively safe environment for learning how to operate in deep space. Relatively safe because it is close enough to home that the consequences of serious problems are manageable in a way they will not be once we are farther out. The crew of Artemis II was part of this iterative process. That their mission was not about science alone, it was about learning, about discovering the practical realities of deep space human operations that simulations and ground testing cannot fully replicate, about understanding how human beings respond, physically and psychologically, to extended time in the deep space environment, about identifying the gaps between the engineering models and the reality of flying in a spacecraft far from Earth with no possibility of quick rescue. They were learning for us all, for everyone who will follow them. Let us take a step back from the science and the mission details and simply sit with the scale of what we are discussing. The Moon is 239,000 miles from Earth, on average. This is far enough that it takes 3 days to reach with current rocket technology. Yes, it is far enough that the communication delay is perceptible, that the Sun appears a slightly different size, that the stars are unchanged from Earth's perspective, but the Earth itself appears as a different kind of object, a planet, a sphere, a world you can cover with your thumb. And yet, in the context of the solar system, the Moon is right next door. The Sun is 93 million miles away. Mars, at its closest, is 34 million miles away, but at its farthest, nearly 250 million miles. Jupiter is 365 million miles away at closest approach. And beyond Jupiter, Saturn, Uranus, Neptune, each progressively farther, each a distance that dwarfs the Earth-Moon gap so completely that it almost doesn't make sense to use the same units. The nearest star beyond our Sun, Proxima Centauri, is 4.2 light-years away. A light-year is the distance light travels in a year, about 5.88 trillion miles. Proxima Centauri is 25 trillion miles away. The Moon is 239,000 miles away. These numbers are so different that they require different orders of magnitude to express. And even when you write them out and stare at them, the true scale doesn't quite register. The crew of Integrity traveled to the Moon. They went farther than any human before them. They were 252,000 miles from Earth, the most isolated humans in history. And from the perspective of the galaxy, they barely moved. They left the surface of one rock and flew to another rock in the same gravitational neighborhood, 2 specks of matter orbiting the same star in the same solar system, in the same unremarkable spiral arm of the Milky Way. This is not a criticism. It is a fact. And it is a humbling one. The universe is so large that the most extraordinary journey in human history is, cosmically speaking, a local errand. And the Moon, that vast and ancient and violent and beautiful world that has hung in our sky forever, is, by the standards of the universe, essentially touching us. What lies beyond the Moon, the genuine beyond, the interplanetary and interstellar distances, remains entirely unvisited by humans. The robots we have sent out there, Voyager 1, now in interstellar space after 46 years of travel, still only about 22 light hours from Earth, still an incomprehensibly tiny fraction of the way to the nearest star, are the only physical objects our species has placed in the genuine beyond. The crew of Integrity was at the edge of the human envelope, and the edge of the human envelope is, at this point in history, the Moon. We have been talking about the Moon as a scientific object and as a human destination, but let us also talk about it as a cultural object, because what we see in the Moon and what we project onto it has shaped human thought and feeling for as long as our species has been able to look up. The Moon has been goddess and god, has been madness. The word lunatic comes from the Latin luna, and sanity, has been the ruler of the tides and the keeper of the calendar. Every civilization that has ever existed has had a relationship with the Moon, has told stories about it, has organized its agriculture and its festivals and its cosmology around its cycles. The Moon is the most reliable celestial object in human experience. It is always there, weather permitting, always changing in a predictable way, always returning to its beginning, always completing its cycle. It is the most visible example in the human environment of cyclical time, of the pattern that ends and returns and ends and returns, the rhythm that underlies the seasons and the tides and the human body's own cycles. All of this was relationship with the near side, with the face, with the features that our ancestors named and mythologized, the seas that are not seas, the mountain ranges visible with the naked eye, the highlands that look different from the Maria. The far side existed in all this time as pure potential, as the unseen, as what the Moon keeps to itself. And now we know what it keeps. We know it as ancient highlands and impact craters and thick crust, and almost no volcanic activity, and a radical departure from everything that made the near side familiar. Yet we know that it is scientifically extraordinary and geologically preserved and radio quiet, and potentially the best place in the inner solar system for a certain kind of astronomical observation. And knowing this does not diminish the mythology. It enriches it. The moon has always been the place where the familiar meets the unknown, where the calendar and the predictable cycles give way to the edge of what we can understand. The far side is, in a sense, the moon's true face. Its scientific face, its geological face, the face that tells the story of creation and destruction, without the overprinting of volcanic activity that partially obscures the near side's record. If the near side is the moon that inspired poetry, the far side is the moon that tells the truth. One of the less discussed aspects of the Artemis II mission is its psychological dimension, not the overview effect or the isolation which we have already addressed, but the quieter psychological territory of long-duration spaceflight. 4 people in a space roughly equivalent to a camper van for the better part of a month. The full Artemis II mission duration was approximately 3 weeks. In microgravity, without the normal cues that organize the day, no sunrise through a window, no gravity pulling you towards sleep at night, no weather, no seasons, no sense of a landscape changing around you. The schedule is maintained artificially, by lighting and by clocks, and by the rhythm of work, but the body's circadian system is under pressure. Sleep is more difficult in microgravity. Privacy is essentially absent. Yet every aspect of physical existence, eating, exercise, hygiene, medical care, is structured and scheduled and documented. And beyond all of this, the constant background awareness that you are in space, that the environment outside the thin walls of your spacecraft is immediately, completely lethal. A micrometeorite impact, a seal failure, a computer error, any of dozens of possible failures, any of which could end everything quickly and absolutely. This is not a constant, acute fear. The training and the procedures and the trust in the engineering manage the fear. But it is a constant background awareness, a low hum of mortal seriousness that is simply part of what it means to be where you are. The psychological selection and preparation of astronauts is extremely rigorous. And the crew of Artemis II were among the most thoroughly evaluated and prepared human beings who have ever lived. But even preparation cannot fully eliminate the psychological reality of deep space isolation. What the research on long-duration spaceflight shows is that the challenges are not dramatic, not madness or breakdown or acute crisis, but a slow erosion of small things. The texture of daily life becomes flatter, the humor becomes drier, the relationships between crew members, which begin warmly, develop the particular quality of relationships that are simultaneously intimate and inescapable. You know each other completely, but you cannot choose to be apart. Yet the strategies that work best involve maintaining purpose and meaning. Keeping crew members engaged, not just with tasks, but with the larger significance of what they are doing. The science, the exploration, the sense of being part of something larger than any individual mission. For the crew of Integrity, the naming of Carroll Crater was a reminder, a spontaneous, unscripted reminder, of why meaning matters in this environment, an act of love and grief in the most unlikely place, creating exactly the kind of human connection that sustains people through difficult times. Let us also discuss one of the more technically fascinating observations that the crew made during the Farside transit, the detection of what appears to be a previously unmapped magnetic anomaly in the southern Farside Highlands. This is preliminary data, not yet published or formally announced, but the instruments aboard Orion registered a localized region of significantly stronger magnetic field than the surrounding terrain, in an area that prior orbital surveys had not flagged as particularly magnetically active. If confirmed, this would be a new data point in the ongoing effort to map the distribution of remnant magnetism across the lunar surface, a map that helps scientists understand both the moon's history and its relationship to the early sun's magnetic field. The moon's magnetic history is one of the more active areas of current lunar research, and for good reason. It connects to fundamental questions about the moon's interior structure, the history of its core, and the timing of its internal cooling. Yet the moon is believed to have had a liquid metallic core early in its history, a core whose dynamo action generated the global magnetic field that magnetized rocks and was then preserved as remnant magnetism when the core cooled and the dynamo stopped. The timing of this process, when the moon's global field was strong, when it weakened, when it finally stopped, is written in the magnetic record of lunar rocks, and the distribution of magnetic anomalies across the surface is one piece of that record. The anomaly detected during the Artemis II transit will need to be followed up with dedicated orbital observations, and ultimately with surface measurements, a magnetometer deployed directly on the surface, measuring the local field strength at a range of locations, building up a high-resolution map of the anomalous region. Yet this is exactly the kind of targeted follow-up that human presence in the vicinity makes easier to plan. The crew observed something unexpected, noted its approximate location, and the data they transmitted will allow orbital planners to design a dedicated follow-up survey. This is the rhythm of scientific exploration. You go, you look, you notice something unexpected, you design the next observation to investigate it. The unexpected is not a failure. The unexpected is the engine. We are getting toward the end of our story of the far side. Though, in truth, the far side story is very far from over. It has been accumulating for 4 billion years. It will continue accumulating for billions more. Human beings are late arrivals to this story, and our role in it is just beginning. And let us spend some time now with the larger question that the mission of Artemis II implicitly asks. What are we doing here? Not in the bureaucratic sense. Not what was the mission profile or the scientific objectives or the budget justification. But in the deeper sense, why is our species sending people to the moon? What does it mean for us as a civilization to reach beyond the atmosphere and place human bodies in places that human bodies were not evolved to go? The simplest answer is curiosity. Human beings are curious. We have always been curious. The urge to see what is on the other side of the mountain, to sail past the edge of the known map, to look through the telescope at the dots of light and ask what they are. This is not a modern phenomenon. It is as old as the species. Every human culture in history has had explorers. It has had people who felt drawn toward the horizon, who could not be satisfied with the familiar. But curiosity alone does not explain the scale of the investment. Space programs cost tens of billions of dollars. They consume decades of engineering effort. They put human lives at risk. Curiosity is necessary, but not sufficient. A second answer is survival. In the long run, the very long run, the span of millions or billions of years that we cannot quite imagine, but that is nonetheless real. A species that confines itself to one planet is a species that will eventually be destroyed by that planet's inevitable catastrophe. The sun will eventually expand. The oceans will eventually evaporate. The biosphere as we know it will eventually end. On shorter timescales, as asteroid impacts and supervolcanic eruptions and other catastrophic events pose real threats to civilization. A species that has spread beyond its home planet, that has established self-sustaining communities on other worlds, is less vulnerable to any single catastrophe than a species that is fully concentrated on one. This is an argument from prudence, from long-term risk management, and it is a legitimate one. But it operates on timescales that make it feel abstract. The sun will not expand into a red giant for billions of years. Civilization-threatening asteroid impacts are rare events measured in hundreds of millions of years. The survival argument is real, but it is not immediate. A third answer, and in some ways the most interesting one, is meaning. Space exploration changes how we see ourselves. The overview effect, that shift in perspective that astronauts report after seeing Earth from space, is not just a personal experience. It has collective implications. The photographs that come back from space exploration, the ideas that are catalyzed by the experience of leaving Earth, the sense of common humanity that is reinforced by the image of our planet from the outside. These have cultural value that is difficult to quantify, but impossible to dismiss. The Earthrise photograph of 1968 is one of the most significant images ever made, not because of its technical quality, but because of what it did to the people who saw it. It showed them something they knew intellectually, but had never seen directly. That the planet is finite, that it is one thing, not a collection of nations and territories, that it is small relative to the universe it inhabits, that it is fragile in the sense of being a specific, irreplaceable arrangement of matter and conditions that can be changed or damaged. The crew of Integrity, returning around the limb of the moon and seeing Earth reappear after the blackout, had this experience again. And when they came home and told their story, they added another layer of testimony to the growing archive of human beings who have seen the Earth from outside and been changed by it and reported back. Now let us take the mission home. After the far side transit, after the blackout, after Earthrise, Integrity settled into the return trajectory, the long arc back across the 250,000 miles of space between the moon and Earth. The 3-day return journey is in some ways the most psychologically straightforward part of the mission. Here, the extreme isolation of the far side is over, communication with Earth has been restored, Earth is getting larger in the window instead of smaller, you are going home. But the return journey is not uneventful. The entry into Earth's atmosphere, re-entry in the language of spaceflight, is one of the most dramatic and demanding events of any lunar mission. Orion, returning from the moon, is traveling at approximately 24,500 miles per hour when it reaches the upper atmosphere. This speed is significantly higher than the roughly 17,500 miles per hour at which objects return from low Earth orbit, because the moon's gravity has added additional velocity during the outbound journey that must now be shed. When Orion hits the upper atmosphere at this speed, the friction between the capsule's heat shield and the air molecules compresses the gas ahead of the vehicle to such extreme pressures that it heats to temperatures of several thousand degrees Fahrenheit, hotter than the surface of the sun in its photosphere, at least briefly. The heat shield, made of a material called AV coat, a honeycomb structure filled with ablative material that burns away slowly, carrying heat with it rather than transmitting it into the capsule, protects the crew from this firestorm. The temperature on the outside of the heat shield reaches approximately 5,000 degrees Fahrenheit. Inside, the crew experiences temperatures comparable to a warm room. This aero capture into Earth's atmosphere is not a simple straight-line deceleration. Orion performs a skip re-entry. It enters the atmosphere. It allows the atmospheric drag to slow it partially, then skips back up into the upper atmosphere briefly before entering for the final descent. This maneuver extends the deceleration over a longer period and allows the heating to be more manageable than a direct, steep entry. It is a technique that exploits the physics of atmospheric flight in a way that feels almost counterintuitive. You partially enter the atmosphere, get slowed down, bounce back out, slow down more, and then come in for the final approach. The parachute deployment is the final phase, a sequence of drogue chutes to slow the capsule initially, followed by the main parachutes that bring the speed down to something manageable for splashdown. Orion is a water landing vehicle designed to come down in the ocean and be recovered by a ship and recovery team. Hit the splashdown itself, the moment when the capsule hits the water and the ocean spray erupts around it and the motion suddenly stops, and gravity, real, full Earth gravity, presses everyone back into their seats for the first time in weeks, is described by returning astronauts as profoundly strange. Weeks of microgravity leave the body temporarily adapted to weightlessness. Muscles atrophy, even with exercise. The cardiovascular system reconfigures to distribute fluid without gravity's help. The brain's sense of orientation recalibrates to an environment without a constant down. And then, suddenly, there is a down again. There is weight. The arms feel heavy. The head feels heavy. Standing up is an effort. The familiar sensation of being held to a surface, of gravity doing its work, feels foreign in a way it never has before. Here's the crew of Integrity, returning from the most distant journey in human history, had been in space for approximately 3 weeks. They splashed down in the Pacific Ocean, were recovered by a Navy ship, and began the process of readaptation to Earth's gravity. This process typically takes days to weeks. The body adjusts gradually, rebuilding fluid balances, restoring cardiovascular function, allowing the muscles to relearn their relationship with weight. They were home. They had been farther than anyone, and they had seen the face that faces away. Let us close this exploration with the far side itself. with what it represents, what it preserves, and what it still has to teach us. The far side of the moon is old, genuinely almost incomprehensibly old. At the surface of the far side highlands is estimated to be approximately 4.4 billion years old, formed in the aftermath of the moon's own formation, solidified from the ancient magma ocean, and then battered by the intensive bombardment of the early solar system. For comparison, Earth is 4.5 billion years old. The far side highlands formed when Earth was barely 100 million years old, when the interior of our planet was still largely molten, when the first solid crust was only just beginning to form, when the conditions for life were not yet possible. There were no eyes in the universe to see the far side form, no consciousness anywhere in the solar system to witness the cooling of the magma ocean, the crystallization of the crust, the beginning of the bombardment that would scar its surface for billions of years. Yet the far side formed in absolute solitude, in a universe that had not yet, as far as we know, produced any entity capable of perceiving it. And then, 4.4 billion years later, a spacecraft appeared. 4 human beings, products of 1 billion years of biological evolution on a small planet nearby, flying around in a metal capsule and looking out the windows. They saw it. After 4.4 billion years of being unseen, the far side was seen. By creatures that had not existed for most of that time, who had not known the moon was there for most of their own species' history, who had not known the far side existed until 67 years ago, who had not built the spacecraft to reach it until 50 years after that. This is, if you sit with it long enough, a remarkable fact. The universe has been going on without witnesses for most of its history. The first stars formed about 400 million years after the Big Bang, the first moment when there was light in the universe, when there was something to see, but there was nothing to see it. Stars burned and died for billions of years in complete darkness from the perspective of consciousness, because consciousness hadn't happened yet. The solar system formed, the moon was born, the Earth acquired its oceans and its atmosphere and its first living cells. All of this without any entity in the universe to experience it, as far as we know. And then, after an almost unimaginably long period of cosmic aloneness, the universe produced a species that could look back at it, that could take instruments and spacecraft to previously unreachable places and look at them with something that was neither ignorance nor indifference. That could stand or float before the face of the moon that has been hidden since the solar system's beginning and say, "We are here. We see you. We want to understand what you are." This is what the crew of Integrity did. This is what the mission of Artemis II meant, beyond the engineering and the science and the budget justifications and the geopolitics. It meant that the species responsible for this extraordinary improbability, consciousness arising in a universe that had been unconscious for most of its existence, was extending its reach, was saying, the far side is not beyond us, the ancient surface is not beyond us, the solitude that the universe has maintained for billions of years is not beyond us. Yet the last thing the crew saw before losing sight of the moon, as Orion moved away on its return trajectory and the moon shrank behind them, was the familiar near side, the face they had grown up seeing, the Maria and the Highlands, and the features that their cultures had named and mythologized. The face of the moon that every human being in history had seen, the only face of the moon that anyone on Earth will ever see from the ground. But they had seen the other face too. They carried that with them. Every astronaut who returns from a significant mission carries something back that they did not go up with. Not data, not rock samples, not the technical information that is the official cargo of the mission. Something more personal, harder to articulate. A revised understanding of something. A memory that will not fade. A piece of the universe that has been incorporated into the self. For the crew of Integrity, the far side of the moon was that thing. The cratered highlands, the thick, ancient crust, the impact basins older than life on Earth, the magnetic anomalies, the radio silence, the Terminator line sweeping across the landscape, revealing hidden complexity and shadow. The cosmic ray flashes in their eyes. The 40 minutes of absolute isolation, Earthset and Earthrise, and the crater named Carol, small and unnamed by any official authority, but real. A physical feature on the surface of the moon that carries the name of a woman who died of cancer in 2020, placed there by a man who loved her, and who had come as far from home as it is possible for a human being to go, and still carried her with him. The far side of the moon is not empty. It is full of things we have not yet understood. Geological mysteries whose solutions will reshape our picture of how the solar system formed and evolved. Scientific resources that will not be fully cataloged for decades. It is full of the ancient record of creation and destruction. It is full of the deep past of the solar system, preserved in stone in a way that nowhere else in the inner solar system preserves it. And now it is full of something new. The knowledge that human beings came here, that human eyes looked at it, that human minds tried to understand it, that human hearts named a small piece of it for love. That will be true forever. However the far side changes, however many more meteoroids fall on it, however many more billions of years the bombardment continues, it will always be true that on a particular day in April of 2026, 4 human beings flew over it and saw it and tried to understand what they were seeing. The universe will not care. The moon will not care. But the record will be there, in data and in memory and in the name of a crater. One small mark, in an ancient landscape that has been receiving marks since the beginning of the solar system. We leave marks. That is what we do. We look at things and we mark them, with observations and names and photographs and the quiet, persistent effort to understand. And then we go home, and the marks remain, and the universe keeps going, and somewhere in the continuing story of matter and energy and time, the fact of our looking is preserved. There is one more thing to say, and it is perhaps the most important. Yet the moon has been with us for as long as we have been us. It pulled the tides that shaped the coastlines where our ancestors learned to fish. Its light illuminated the nights of our earliest wanderings. Its cycles organized the first calendars. Its face has been a canvas for human imagination since before imagination had words to express itself. It is the most familiar celestial object in human experience, the most intimately connected with human biology and culture and history. And we have been looking at half of it. Only half. For 100,000 years of human history, for all the poets and the farmers and the astronomers and the navigators who looked up at the moon and felt something, they were looking at half of it. The other half was there, had always been there, had been suffering its billion-year bombardment and preserving its ancient geological record and maintaining its radio silence, unseen and unregarded by anyone in the history of our species. We have begun very recently to correct this. We have begun to see the whole moon. Not fully. There are still things about the far side we do not understand, features we have not mapped in detail, geological questions we cannot answer without surface samples from locations we have not yet visited. But we have started. The crew of Artemis II was part of this beginning. They flew around the moon and saw the face that faces away, and they were changed by it, as people are changed by seeing things they have never seen before. They came back, and they told their story. And their story became part of the record, part of humanity's slowly growing understanding of the world it lives in and the worlds it lives near. The far side is no longer unknown. It is known, beginning to be understood, beginning to be visited, beginning to be named. Carroll Crater is a small mark in an enormous landscape, but it is a mark, and marks accumulate, knowledge accumulates. Understanding deepens. The half of the moon we never saw is becoming the half of the moon we are learning to read. And what it is telling us, in the language of ancient craters and thick crust and asymmetric geology and preserved bombardment records, is the story of the solar system's beginning. The story of violence and formation, and the slow cooling of a molten world into the stable landscape of today. Yet the story that Earth cannot tell, because Earth has been too busy living, too geologically active, too biologically complex, too thoroughly rewritten by 4 billion years of life and plate tectonics and erosion, to preserve the original record. The moon kept the record. The far side kept the oldest and most complete version of it. And now, slowly, we are learning to read it. That is what 4 astronauts found on the far side of the moon. Not an alien landscape, not a secret kept from us by the cosmos. Just the oldest record in our neighborhood, waiting to be read, finally being read, by the newest kind of consciousness that has ever existed in the solar system. We are the readers. This is the text, and we are only just beginning to learn the language. Now, there is a particular quality to the light on the moon that we have not yet discussed, and it seems right to end with it. It is something that astronauts consistently mention when they try to describe what the moon actually looks like, in person, up close, in a way that photographs fail to convey. The moon's surface scatters light in a specific way. The fine powder of the regolith, those billions of tiny, jagged particles ground from ancient rock by billions of years of meteoroid impacts, scatters sunlight back toward the source. It is called a retroreflective surface. When you look at the moon from space, at certain angles, the area directly opposite the sun, the region your shadow points toward, appears unusually bright. The sunlight bounces back at you from millions of tiny facets, each one angled to send the light in the direction it came from. This means that when an astronaut stands on the moon and looks at their own shadow, the area around the shadow appears brighter than the surrounding terrain. Their shadow has a bright halo. They are, in a sense, looking at a spotlight that follows wherever they look. The whole lunar surface behaves this way, acting as an enormous, low-efficiency mirror that sends a fraction of the sun's light back in the direction of the sun. This is why the moon is as bright as it is. Not because it is actually a very reflective surface. It is not. It reflects only about 12% of the light that hits it, about as reflective as asphalt, but because of this retroreflective effect. From orbit. This creates a particular quality of the light on the surface that astronauts find difficult to describe. The terrain does not look like terrain under a sun that is somewhere else in the sky. It looks like terrain under a sun that is everywhere at once, with shadows that are darker and more absolute than any shadow on Earth, and highlights that are brighter and more concentrated than any highlight on Earth. It is a landscape of extremes, of absolute shadow and brilliant light, with nothing soft in between. No atmosphere to scatter the light, no clouds to diffuse it, no reflected light from surrounding landscape to fill in the shadows. The far side, seen from Orion, had this quality. The craters were pools of absolute darkness, if their floors were shadowed. The crater rims were bright as diamonds where the sun caught them. And between these extremes, in the crater floors that were in partial light, in the gentle slopes of the highlands, in the ancient, battered terrain that stretched in every direction, the surface had a gray-brown quality that was subtly different from anything on Earth. Not beautiful in the way that an Earth landscape is beautiful, not with the lush complexity of life or water or weather, but beautiful in the way that very old, very simple, very honest things are beautiful. Beautiful in the way of something that has been what it is for a very long time, without apology, without modification, just sitting there in the cold dark, absorbing the impacts and recording the history and waiting for someone to come and look. They came. They looked. And now they have told us what they saw. The far side of the moon is not empty. It is full. It is full of the past, and of silence, and of the ancient geology of creation, and of the record of impacts that shaped our solar system, and of the scientific mysteries that will occupy researchers for generations. And now it is full of something new. The knowledge that human beings have been there, have looked at it, have named a small piece of it for love. We are part of the moon's story now. We were always part of it. The moon shaped Earth, and Earth shaped us. And we carry the moon in our biology and our calendars and our poetry and our tides. But now we have been there and seen the face that faces away and carried that knowledge back. The circuit is closed. The story, which was never just a story about the moon, is a story about us too. The moon has been watching us for 100,000 years. And it has been watching our fires and our cities and our wars and our love and our art and our questions. And now, at last, we have turned around and looked back. We have gone to it, around it, over the face it hides from us, And we have seen it, not just as an object in the sky, but as a world. A specific, detailed, ancient, violent, beautiful world that happens to be our nearest neighbor in space. And what we found there, what the crew of Integrity found, flying over the far side in the last hours of the moon's long privacy, is the same thing that every genuine exploration eventually finds. Not what we expected, not what we feared, not what we hoped for. Just the truth. Just the complicated, specific, astonishing truth of a world that has been there all along, doing what worlds do, carrying its history in stone, and waiting for someone curious enough to come and look. They came. They looked. We know more than we did. And the moon, indifferent and beautiful and ancient and close, continues to shine.